And the covariance between this and that, because this is a constant, we can take it outside the covariance, become lambda k covariance of xt, but we know that the covariance between xt minus k is the same as the variance. And this means that the variance of xt minus k, we know it from previously, remember, we have spoken about it, it's equal to this guy. So it seems that the covariance between xt and xt minus k is equal to what? This variable over here, right? Which is lambda k sigma squared 1 minus lambda 2k over 1 minus lambda squared. Now, I wanted to give you this as an in-class problem, but since we need to go through many things, and as I thought that this is important, I'm gonna solve it for now. If we want to look at, you know, a, where a is a constant to the power t, and t goes to the approaches plus infinity. If the absolute value of a was smaller than 1, that means that a is between minus 1 and 1. Okay, what happens to a to the t? Does it go to 0, infinity? So, you know, like if you multiply 0.5 by 0.5, is it greater than 0.5 or smaller than 0.5? Well, it's smaller. It's actually 0.25, which is quarter. And therefore, as you multiply a, you know, a constant that is smaller than 1 with the same constant that is smaller than 1, things are going to approach 0. Now, if we have 1 to the power 1, you know, 1 to the power infinity is 1, right? So 1 times 1 times 1 times 1 is always 1. So this is 1. And when we have minus 1, the problem with minus 1 is sometimes minus 1 times minus 1 is plus 1. Minus 1 times minus 1 times minus 1. So minus 1 to the power 3 is minus 1. So the problem here is that we don't know. It is somehow either 1 or minus 1 depending on t, if t is even or odd. Or sometimes, you know, the problem with t is that sometimes it might take some irrational numbers, so we don't really know how would minus 1 behave. It's like when we have, you know, minus 1 to the power 0.5, for example, right? It becomes some number called I, which is a complex number, which is beyond the scope of this module. But anyways, I just want to tell you that when a is minus 1, we are unsure about it. When a is greater than 1, so if we have any two numbers multiplied by one another that are greater than 1, things become going to infinity. When it is minus 1, it is undetermined as a case of a equal to minus 1. So the answer to this question is that if a between 0 and 1, it is 0. When a is equal to 1, it is 1. I think this is not true. This is unknown. It is undetermined, as I told you why, because we are expecting t to be also a rational number. If t is only like rational number or natural number, then this might be minus 1 or 1. But here we're assuming that t might be an irrational number. And when a is greater than 1, this becomes plus infinity, and it is unknown if a is smaller than minus 1. So let's study the stability conditions. There is very important thing that, okay, where would e to the expectation? Remember that what we spoke about covariance stationary. A covariance stationary is a process where we believe that the expected value of the process is equal to a constant and not function of time. Is this a constant, not function of time? Well, the answer is no, obviously, because you can see that there is a t over here, which is lambda to the t is a function of time. And therefore the expected value of the process is not equal to a certain constant that is not function of time. And this means that an autoregressive order 1, as it is what? It is not a covariance stationary. There is some link between them. And we want to know where would this approach as t goes to infinity. So where would this lambda t goes as t goes to infinity? If lambda in absolute value was smaller than 1, this goes to what? Alpha over 1 minus alpha, right? So let's study the limits of the autoregressive order 1 process. So we have mentioned that here we have mentioned the fact that we have this condition to hold, which is the expected value of the process of the autoregressive order 1 process is equal to alpha 1 minus lambda t over 1 minus lambda. Remember that, is this an autoregressive of order 1 process? Is it a covariant stationary process? The answer is no, because it doesn't fulfill the assumptions we hold about the autoregressive. Let's say yt is an autoregressive order 1, then we know that e of yt should be equal to what? Mu, which is a constant I'm gonna call it mu of y because it is a which is the mean of y. It is a constant that is not a function of time. But here, as you can see, that the expected value of the autoregressive of order 1 process is a function of time because of this. But what happens when t goes to infinity and lambda is between 0 and 1? This goes to alpha over 1 minus lambda if lambda in absolute value is smaller than 1. Because if lambda in absolute is smaller than 1, then we don't have a problem over here, and this becomes what? A constant, which is we're gonna call it mu of x. So I'm gonna call it as a mu of x, which, as you can see, it's not a function of time anymore as time goes to infinity. When we look at the variance is also the same principle as it is a constant, so it doesn't fulfill the same assumptions of a process that it is covariance stationary, which is equal to sigma squared of y, I'm gonna call it. And this goes to what? If t goes to infinity, this goes to 0, condition on the fact that lambda in absolute value is smaller than 1. So this becomes sigma squared over 1 minus lambda squared if lambda in absolute value is smaller than 1. And talking about the covariance, we also showed that the covariance of xt minus k is equal to the covariance of xt plus 1. Remember that this is due to the stationarity of the process. And this is equal to what? The covariance between xt and xt, we're gonna call it lambda k. We expect, remember, that the covariance of yt minus k, or yt plus k, which is a covariance, should be what? A function of k and not a function of time. Okay, it should not be a function of time, and therefore we can see that here it is a function of time, and therefore it is not a covariant stationary process for all of these reasons. Now, if lambda is between 0 and 1, or an absolute value, which is lambda, this is the same as lambda between minus 1 and 1, then we think that this goes to what? To sigma squared lambda to the k over 1 minus lambda squared, and this is not a function of time, and you can see that it is only a function of what? Of k. So as t goes to infinity, this is a function of k, and therefore the covariance between xt and xt minus k is only a function of k. Through all of this, we call this to be the stability condition, which is what? The lambda to be between minus 1 and 1, we call it to be the stability condition. So the stability condition is when the absolute value of lambda is is smaller than 1. Now let us take this into action. So we have this, you can see over here is an autoregressive of order 1 process. You can see it over here, where lambda is given by plus. You see this is a plus sign, and therefore lambda is equal to plus 0.8, which is in absolute value is equal to 0.8, which is smaller than 1, and therefore we believe that this is to be a stable autoregressive of order 1 process. Now here we are assuming that x0 is equal to 0 and lambda t to be a white noise, which is, it could be an IID that follows a normal random variable 0, 1. You can see that e of xt, what did we say about it? It's equal to alpha over 1 minus lambda. What is alpha? Alpha is equal to 2. Here this is our alpha, this is our lambda. So alpha is equal to 2, so it's 2 over 1 minus lambda 0.8, which is equal to 10. And as you can see, if we simulate the process, what is the mean of the process? The mean of the process is 10. Okay, and the variance is 2.8. So how far are the points from one another is about 2.77. Okay, somehow. Okay, so you know what we mean by the variance, so I'm not gonna go into the details. It's just something related to the normality of the distribution, that is 95% of belong between 3 sigma mu plus 3 sigma and minus mu mu minus 3 sigma. So 95% of the data belongs here, right? So I'm not gonna go into the details, but you can refer to this. Now, talking about time series stationary stochastic process, we know that xt is equal to, you can see here there is something called a trend, where we have this t over here. And we are assuming that it is somehow fulfill the lambda smaller than 1, which is stability condition when we are talking about the autoregressive of order 1. Now remember, if we replace t with t minus 1, then we replace everything by t minus 1, t minus 1, rather than t minus 1, t minus 1 minus 1 is t minus 2, and t minus 1. And we do this this recursive relationship. It turns out to be that if you fulfill you make things a bit clearer, and you put everything into account, you will have this kind of structure. Now let's put, rather than xt minus 2 over here, xt minus 3, and things become even more complicated. But however, you can see that there is a certain recursive relationship. Here we have somehow a geometric series. Here we have somehow, so for example, this is t minus 1, then we have 1 and 1 are the same over here, 2 and 2 are the same over there. So we know that there is a certain relationship between things. And here you can see that this is 3 and 3 over here, 2 and 2 over there. So you can see that there is a relation. This is to the power 1, 1 and 1 over here, and lambda to the power 0, 0 and minus 0 over there. So you can see that there is a certain recursive relationship between one of the things, and basically we can write this as follow, right? So this is what we mean by that. Now we can do this to up till k minus 1. You will see that we have relation xt and xt minus k, and we have this relationship. Okay. Now if you go to your formula sheet, you will see that I added two sum series, which is a sum series of j lambda j from j equal to 0 to t minus 1, and it is equal to this. And the other one that I added is this one, which is the sum of from t minus j lambda j from j equal to 0 to t minus 1 is given by this formula over here that you see in front of you. And here is the proof of it, how to prove that this is equal to that. Okay, so in case anybody is interested. But however, I'm expecting you to know these stuff, and therefore I'm not gonna go through the details. If you have any concern about the proofs, you can come to my office hours. Okay, so let's go back here. And remember, we were talking about we have spoken about these things in connection to one another. And basically, if you continue doing this to t minus 1, you will see that we're left with x0 over here. So the expected value is given by the same way we have done it previously. So the expected value of this is going to be the expected value of each and every one independently from one another. This is a constant, this is a constant, so we're leaving them as it is, and this is a constant, so we're leaving it. But we're going to be assuming that x0 is 0, so this goes to 0. So we're assuming this will be going to 0, since x0 is 0. And we know that this is what? This is 0, right? We know that this is 0, and therefore this also goes to 0. Everything goes to 0 here, and we're left with this. Okay, so we're left, if we remember that the sum of this is a geometric series, so 1 minus lambda, and we know the sum of this from the formula sheet is given as so. So this is the same as equating it, almost equating it with what? As t goes to infinity, this becomes almost, if t goes to infinity, this becomes almost like 1 minus 0, since we know that lambda t is going to 0 here. You see that this lambda t is going to 0, and we know that this is going to 0 as t goes to infinity, and we're left with this. So, sorry, and also this t goes to 0, so this is also 0 because of the lambda t. Even if x0 was not 0, this goes to 0 because lambda t is going to 0. So basically we're left with this. So I said here, you can see that I said almost. This means that almost when t is large, maybe I must mention here, when t is large, and this becomes gamma t over 1 minus lambda plus alpha, which is a constant. So you can see that this looks like a constant over here times t plus another constant, because not a function of t. So this becomes the expected value of the process, of a trend process, is at plus b, which is very kind of expected. So what we're expecting is the following. So if you have here a random variable, and you have here x and y, what we're expecting is that the expected value should be a certain straight line, where we know that the slope is equal to a, and the intercept is equal to b, and basically the process goes something like that. Okay, this is a process, but the expected value should be somehow a straight line, This is what it's telling you. Obviously, when we are